Chapter 5 review. We'll start with area between curves. So first example, find the area of the region. Find the area of the region bounded by the given curves. Bounded by y equals 20 minus x squared and y equals x squared minus 12. So two parabolas, one open up, one open down. We need to sketch them roughly. And before we sketch them, I need to find the intersection, where they cross each other, the points of intersection. So set them equal to each other, like a substitution. Put everything with x squared on one side, and you're going to have 2x squared equals 32, divide by 2, x squared equals 16, x equals plus minus 4. We need those points as pairs, so if x is 4, substitute in either one of them, and you get y is 4, and if negative 4, y is also 4. So the point where they intersect the two parabolas is 4, negative 4. So the first parabola, 20 minus x squared, opens down. And let's say this is 20 right here, so it opens down. The second parabola has y-intercept negative 12. So let's say somewhere over here, and it opens up. So this point here, it's negative 12. We know the points of intersection. Well, let me redraw this again. So they intercept at points somewhere here and here. So we have something like this. So this is the graph of y equals x squared minus 12, and the other one is y equals 20 minus x squared. Now, the region between them is this. To find the area, we have a formula. The area between two curves is integral from a to b, f of x minus g of x dx, where f is above. That's very important. If they cross multiple times, you have to break the region down to several regions. So let's substitute here. X is from negative 4 to 4. The graph above is 20 minus x squared. The graph below is x squared minus 12 dx. And it's easy to combine like terms and evaluate 512 over 3. So you should get a positive number for the area. Example 2. This time the region will be a little different. Find the area, same thing, bounded by the curves x plus y equals 0. And the other curve is x equals y squared plus 3y. Always helpful to draw a picture. So even though your test is online, you should draw a picture of your graph to see the region, because in this case, we'll see the region will have curves from the left and right. First, the line. I can rewrite this line x plus, I have to find the intersections, of course. So let's do that. Where they intersections. So y squared plus 3y is equal to x, which is equal to negative y. If you use a substitution, y squared plus 4y equals 0, factor y, and you get 2 points. Y equals 0, y equals negative 4. Of course, you have to write them as pairs. So if y is 0, plug in either equation, you're going to get 0. And if y is negative 4, plug it in, you get x4. So these are the 2 points of intersection. 0, 0, the origin, and 4, negative 4. So let's say it's somewhere here. So now we can graph the line first. X plus y equals 0. We can rewrite it as y equals negative x. It's the same line. So it has a slope negative 1. So here's that line. That's the line y equals negative x. And the parabola, it's sideways. It opens to the right. You can have a table, or you can just make a graph going through the 2 points of intersection. Where's the region? The region is this. Now you notice that the curves now are not above and below, but to the left and to the right. So to find the area in our formula is integral from C to D, x from the right minus x from the left, dy, everything in terms of y. Or you can think about the graph to the right minus the graph to the left. Everything is in terms of y, so the boundaries are the boundaries for y. So our point here was 4, -4, and that was 0, 0. So the y changes from -4 to 0. The graph to the right is the line. In terms of y is -y, because it was x equals -y. Okay, so let me write this down. That's the same as x equals -y. This is our right curve, minus the one to the left in terms of y is y squared plus 3y. It was given that way, x equals to that. And so dy, combine like terms, and integrate 32 over 3. You should always get positive number for the area. Now volume. Example 3. Find the volume of the solid. Find the volume of the solid obtained by rotating the region bounded by the given curves. Bounded by, and these are the given curves. Y equals 2x, y equals x squared, about the x-axis. Always graph the region. So the region is between the curves y equals x squared. Here's the parabola, even though we only need the right half. And the line y equals 2x is a line with a slope 2 going through the origin. So our region is this. Oh, perhaps I should highlight it. This is our region. We can find point of intersection, always important. Intersections, set up a system. So we have y equals x squared, but y equal to 2x. So put everything on one side, factor out x, and solve for x. X equals 0, x equals 2. Those are the x-intercepts. So if x is 0, y is 0. And if x is 2, y is 4. So these are the 2 points. 0, 0, we knew that one. And that point here is 2, 4. My picture is not drawn to scale, but that's okay. So how are we going to show the solid? We're rotating about the x-axis. So the symmetrical graph here would look like this. And if you want to show this as a solid, it's like a funnel. Okay, let's have a cross section anywhere. Now, we can use different methods. So we can do the washer method, or we can use the cylindrical shells. So let's try the disc washer method. Disc washer method, that was 5.2, where we slice the shape anywhere, and we see the cross section is a washer or a ring, and our formula is integral from A to B, the cross section area, dx, and now everything has to be in terms of x. How is x changing here? X is from 0 to 2. We're looking at the region, and let's write down here, what is our outer radius? So outer radius in our cross section. Our outer radius would be at the random point xy would be that. This is, let's call it R2. Outer radius R2 is equal to the y coordinate of that point, which is equal to 2x, because it's on the line y equals 2x. The inner radius, let's call it R1, And the inner radius is, I'm going to use red, is this one. This is R1. And that's equal to y, but a different y. It's on the curve. So that y is equal to x squared because it's on the graph y equals x squared. So go back to our formula. Maybe we should write down what a of x is. Pi r2 squared minus pi r1 squared. And we can substitute, factor out pi. R2 is 2x squared minus r1 is x squared squared. So that's equal to pi 4x squared minus x to the fourth. It's okay because we are from 0 to 2 here. Go back in our integral and we have pi and 4x squared minus x to the fourth dx. Evaluate this, 64 over 15 pi. Positive number for the volume. Okay, we could have done cylindrical shells and we'll get the same answer here. All right, another example. Let's see, did we number problems? Yeah, examples. Okay, example 4. Example 4. Here, we're gonna set up but do not evaluate an integral for the volume set up but do not evaluate an integral for the volume of the solid obtained by rotating the region bounded by the given curves, and the curves are y equals x to the third, y equals x squared, about y equals 1. So it's a little different now. We don't have the axis of rotation being the x or the y-axis, but it's a different one. So we're going to sketch the region first. And the region is between two curves and where the intercept, that's important. These two curves, it's easy. Y equals x to the third, y equals x squared. So if you set them equal to each other to find the intersection, that's what we're doing here. Find the intersection. You have x to the third minus x squared equals 0. X squared is factor x minus 1. So x equals 0 and x equals 1 are the 2 points of intersection. So 0, 0, and 1, 1, if you plug them in. So here's the 0, 0 right here. And this point here is 1, 1. Now we need to label the curves. The one that's steeper is the cubic, and the less steep right here is the quadratic. The region, our region is this little crescent here. Okay, so we are rotating this region around the line y equals 1. So here's the line, y equals 1. So draw the symmetrical shape. Not quite. Okay, so doesn't look very good. Let's do it again. Okay, a little bit thinner. So this is a symmetrical shape. And then show that this is a three-dimensional solid. And it's like the previous example, but going to the left. So if we slice this with a plane perpendicular to the axis of rotation, so vertical plane, we're gonna have the cross section being a washer. So let's write this down. The cross section is a washer or a ring. So we need either inner radius and outer radius. So let's demonstrate the inner radius at a sample point. This is the inner radius, that's R1. Or R2 would be all the way down to the other curve, that's R2. You can show them in the region. Yeah, perhaps I should do this. Let's do this. Let me show the inner radius over here. So that's R1, and the outer radius goes all the way down here. Okay, so R1, the inner radius, is 1 minus x squared, because all the way down here is 1. All the way from here to here is the y-coordinate, our sample point, right? That's the y-coordinate, which in the inner radius is equal to 1 minus x squared. For the outer radius is 1 minus x to the third. Now the volume is equal to pi integral, everything in terms of x, and x is from 0 to 1. And we have, how do we find the area of a washer? So it's pi outer radius squared minus pi inner radius squared dx. All right, so it says set up but do not evaluate, so we're just gonna leave it like this with this impression. All right, example 5. Set up but do not evaluate an integral for the volume of the solid, so the same thing, set up but do not evaluate an integral for the volume of a solid obtained by rotating the region bounded by y equals cosine x, y equals 0, x equals 3 pi over 2, x equals 5 pi over 2, about the y-axis. So we have to sketch this. We have a cosine graph. So we know the cosine behaves like this. Okay, so where is 3 pi over 2? So pi over 2 is right here. 3 pi over 2 is an x-intercept. And 5 pi over 2 is the next one. So here's our cosine curve. And this region is bounded between y equals 0, which is the x-axis, and 3 pi over 2, that's the vertical line, and 5 pi over 2 and the x-axis. So the region is actually this little mount, this little hill here. If we rotate this around the y-axis, about the y-axis, the symmetrical region would be this hump over here. So show that this actually is solid. We can show it's a solid. It's like a bagel with a very large hole in the middle and it's sliced in half. So we're going to use method of cylindrical shells. Most of the time when your solid has a hole inside, it's easy to use cylindrical shells. So a typical shell would be upside, going straight like this. Typical shell would be, let's see here, I went too far. Typical shell would look like this. Okay, so we'll be straight up. We're going to use the method of cylindrical shells here. So the method of cylindrical shells uses shells nested in each other to fill the solid. So a typical shell we'll have radius, I'll spell it out, radius equals 2. Okay, what is the radius? Here it is. This is the radius. And if this is a sample point xy, then the radius is x. So radius equals to x. Then the circumference is 2 pi x. And the height, this is the height. Isn't the height the y, which is cosine x? So we have everything. Will be simple. The volume, here's our formula, from A to B, 2 pi x f of x dx. Again, we use that formula whenever the circumference is 2 pi x, so we call this is the circumference part. And this is the height. And dx is the thickness. Now, if the solid does not rest on the x-axis, the height may be different. It may be the difference between the y-coordinates of two curves. But in this case, the height is all the way down to the x-axis. So, to continue substitute, what is our boundary here for x? Our region is from 3 pi over 2 to 5 pi over 2, 2 pi x. And what's our f of x? That's the cosine curve, so cosine x dx. It says to leave it the integral without calculating. So a quick review of some formulas in this chapter 5. They're important. So review of formulas and concepts. We had a lesson on work being done. So work is integral from A to B, f of x dx, where f of x is the force. Then we had a lesson on average value of a function that's continuous. And that was 1 over b minus a integral from A to B, f of x dx. Then we had mean value theorem for integrals. So it goes like this. If f is continuous on some interval from A to B, then there exists some number c in the interval from A to B such that f of c, the value of f at that point c in the interval, is the same as the average value of the function. It was like the question of if the average temperature during 24-hour period is 76 degrees, is there a time during this period where the temperature reached that? And we had a theorem that says yes, there's at least one point where the temperature can reach exactly the average temperature. And then go back and review the two methods of finding volume. So we had disk washer method. I used this in the first two examples. And that is when we have some function f of x being rotated. We have a region actually, a region which we rotate around a horizontal axis. So it doesn't have to be the x-axis. So we have something like this. So think about a vase sideways. And in this case, our formula is integral a to b, a of x dx, where a of x is the area of the cross-section. I'll write this down. That's the area of the cross-section. Whether the cross-section is a circle or a washer, ring, it doesn't matter. Whatever it is, you calculate it. So that was the method, disk washer method, if you rotate around horizontal axis. If you rotate around a vertical axis, and again, doesn't have to be the y-axis, I guess I'll do X and Y, but it doesn't have to be as long as it's vertical. And so we have some kind of a curve here, and here's the symmetrical. So we have like a vase straight up. The volume in this case is integral from C to D, A of y dy. So everything here in terms of y, if you're rotating around the y-axis. In the first case was in terms of x, because you rotate around the horizontal axis. So C and D are on the y-axis right here. A and B are on the x-axis. So regardless of what the cross-section is, so A of y, let me write this better. A of y is the area of the cross-section, being this a circle or a washer ring. So that's the first method. That was 5.2. And then we have the cylindrical shells. So cylindrical shells method 5.3. So we want to distinguish. There are many cases where you can use either one, but there are again some cases where you have to do one or the other. So here I have some kind of graph here. I'm rotating it. And we have some solid, it could be shallow inside, and we're using cylindrical shells to fill it in. The volume, in this case, if we have a vertical axis here. Now what's different here is everything is in terms of x, even though we're rotating around a vertical axis. 2 pi x, f of x, dx. Again, that f of x is the height. And it may not be f of x. It could be the difference between two functions, f and g. So you have circumference, height, thickness. And lastly, if you're rotating around a horizontal axis, and here is a solid. So this is here y. I'm gonna write down y-axis, but it could be any vertical axis. Everything is in terms of x. But here, if I have rotation around the horizontal axis in our formula, C to D, everything will be in terms of y. So things kind of flip here, f of y dy. So very important to distinguish those two methods. And this concludes the review for chapter 5.